Hi Abdul. We'll wait for some more time, and then we'll start the session.
Uh, yes, sir. Just now only I got the audio. Now it is
Yeah,
okay.
yeah.
Yeah.
I just allowed.
First your voice I got it, but my mic was mute. Now only I got it.
Yeah, I allowed your microphone
Okay. Okay, sir. Thank you.
now. See if I have last week's. All right, let's start the session. Hello, everyone. Welcome to the 12th weekly discussion and outlining session of the NPTEL course on concrete technology, NOC24-CE46, which is taken by Professor B. Bhattacharya of IIT Delhi. I am Ashirbad Satpathy. I'm a PMRF research scholar at IIT Delhi. And what I do is I take this weekly discussion sessions of 2 hours where we solve the problems that were given to you in the previous week's assignments, and you have already and the ones that you have already submitted the answers to. I mean, the only the assignment questions of which the deadline has already passed. And we also take up any doubts that you might be having regarding the previous week's lectures. There is another teaching assistant to this course. His name is Devojyoti. He usually takes his weekly sessions of 2 hours on Saturdays from 6 to 8 p.m. And I take my sessions on Mondays from 6 to 8 p.m. And I would also like to inform you that this is going to be the last weekly session for this course. We'll have another extra session of just 1 hour on 18th of this month from 6 to 7 p.m. All right. And regarding the previous week's lecture sessions, I have already pasted the link of the video in the chat section, and the lecture slides that we used during these sessions. I have uploaded those to the OneDrive folder, the usual OneDrive folder, and I've shared the link in the chat section as well. You can check it out if you want. All right. In today's session, we'll be discussing the week 11 assignment 11 questions. These questions, the week 11 lectures were regarding corrosion initiation and propagation, cracking of concrete, modeling of cracking and modeling of corrosion in concrete, and those concepts related to the durability aspect of concrete structures. And after that, high strength concrete, its preparation, the factors affecting high strength concrete, the different materials that should be used, and the way the design of the mixture of concrete in order to achieve higher strengths was also discussed with you. And these assignment 11 questions were regarding those concepts of the course. And at the end of this session, we'll also take up any doubts that you might be having regarding the week 11 lectures. The first question was Stern-Gary constant B in linear polarization resistance method is which of the following? It was probably the first lecture of this week. Stern-Gary constant B in linear polarization resistance method of, determination of the corrosion rate. Which of these is the correct answer to this question? Can someone please answer? I've allowed your microphone, so you can just unmute yourself and speak, or else you can raise your hands if you want. I'll respond to you.
Yeah, it is first one. B equal to beta A BC divided by 2.303 bracket B A plus BC beta A plus beta C
Right.
close bracket. That's the first one.
Okay. Yeah. Yeah, that's the correct answer. It's the first one in these options. Yeah. The first option is correct. In fact, the answer is beta A beta C divided by 2.303 times beta A plus beta C. And beta A and beta C are Diffels constants. This is a pretty straightforward question. Beta A, beta C are being Diffels constants. The Stern-Gary constant B is calculated by this equation. All right. The second question is, pitting corrosion happens due to the admixed chlorides present in the concrete. Is this a true or a false statement? Pitting corrosion happens due to the admixed chlorides present in concrete. What is admixed chlorides?
The answer is false.
It's a false, yeah,
Piston
it's a
piston
false
corrosion
statement.
happens due to if it is a seawater and all this is a contact with the seawater and all these things, then the pitting corrosions happens normally. This is not because of the admixer.
Right, right. Very true, Abdul. Thank you. Yes, that is the correct answer. So, what is admixed chlorides? The chlorides that is already present in the concrete mix at the time of mixing itself. It could come from the mixing water. There could be high amount of chloride ions in the water. It could come from using certain admixtures which have a high chloride content in them. So, majorly these are the two sources of chlorides, admixed chlorides in concrete. When there are admixed high amount of admixed chlorides in concrete, it won't cause a pitting corrosion. It will result in a uniform, I mean, rather uniform loss of um, mass of the steel rebar. So the corrosion will be throughout the rebar length rather than at a single point. Pitting corrosion is when the loss of cross section of the rebar is localized in nature. It is happening at a certain location, and at that particular location, the I mean majority of the cross section of the steel rebar is lost. It is corroded, while the rest parts of the rebar is more or less intact. So that results pitting corrosion results from majorly from chloride ingress. What is chloride ingress? It could and I mean the intrusion of chloride into the concrete microstructure from an external source. It could come from, as Abdul mentioned rightly, it could come from seawater, or I mean the vapor or the splash in the coastal areas. So water splash, vapor in coastal areas, or it could also come from, let's say, any chemical exposure, soil contaminated with chloride, um, rich water or something of that sort. Any external source that is providing chloride ions inside the concrete. When these chlorides come inside the concrete, they cause pitting corrosion. The pitting corrosion is a kind of a localized corrosion, localized loss of rebar.
Where there is lack of cover, that also it will affect. If it is very close to the surface of the concrete, that mean if it is not sufficient cover for the reinforcement, that case also in that local portion it will affect also, isn't
Right,
it?
right, yes. So I mean the amount of concrete cover governs the rate of corrosion, or the duration at which the corrosion will initiate. It is just a safety against, you're just taking a safety measure against the corrosion. It is not restricting the corrosion, it will delay the corrosion. So the cover of the concrete will only determine the duration at which, the age at which the corrosion might take place inside the concrete. But if corrosion has to occur, regardless the amount of uh, the cover that you provide, it will take place. Chloride ingress, it will take place in the manner of a pitting kind of a corrosion. In case of admixed chlorides does not depend on cover or any other factor, because you are already providing the source of chlorides inside the concrete at the time of mixing the concrete itself. So it, regardless of the amount of cover you provide, it will take the corrosion will occur. And since chloride induced corrosion is a rather faster process, it takes place very fast as compared to carbonation induced corrosion. So admixed chlorides is the worst case scenario that could occur in concrete, because you're already providing chloride ions inside, large enough chloride and ions inside the concrete. So even if everything else is very good, every the exposure conditions are good, the structure is not even in a coastal region or not exposed to very severe or harsh conditions. If the concrete cover, the structural aspects, the rebar, everything else is pretty good. Still, since the chloride itself is present in the pore water, it will affect the steel rebar. It will cause corrosion in the steel rebar, right? So, in case of admixed chlorides, a more uniform loss of rebar cross section. So pitting corrosion, the coming back to the main question, pitting corrosion occurs in the case of chloride ingress and not admixed chlorides, right? Yeah, I have taken these two view graphs. One is a pitting corrosion and the other one is due to admixed chlorides. Can you guess which one is which? I've not mentioned which one is a pitting corrosion and which one is.
That is the second one, that bottom, that is localized. That is portion is badly affected.
Yes, this is a localized kind of a corrosion.
Yeah.
So this could happen due to, since this is towards the bottom of the structure, this could be coming in contact with splash of water or any other source of water coming from the bottom side of the structure. So this is a pitting corrosion, right? But in this case, the first case, you see that the rebars are corroded, but there is more or less an uniform loss of rebar cross section across the concrete. All the rebars are corroded more or less uniformly, and this is due to admixed chlorides. So sometimes it is difficult to distinguish between whether the corrosion, when the corrosion is uniform in the all the rebars, it is hard to distinguish as to what could be the source of corrosion. Could it be due to admixed chlorides or could it be due to carbonation? And then it is recommended that you look at the lifespan of the structure at which you are assessing the condition of the structure, because carbonation induced corrosion is a slow process. So, typically in the normal cements that we use, carbonation induced corrosion is a slow process. So, and at the same time, chloride induced corrosion is a very fast process. So, if the rebars are uniformly corroded and the corrosion has already occurred in a very short span of the construction, after the construction has taken place, like within 5 to 10 years, then most likely this could be due to admixed chlorides. And once you have guessed like what could be the source of this corrosion, you can take up samples from the structure and you can run some chemical tests by which you can measure what is the chloride content present in the pore solution or in the powder of the concrete, and based on that you'll be able to guess what could be the concentration of chlorides in the concrete mix, and by that only you'll be able to tell which is the source of the corrosion. Is it due to admixed chlorides or is it due to carbonation, right? But pitting corrosion, it's pretty simple. You can guess it by just looking at the rebars. The rebars will be corroded look in a localized manner at a certain section of the rebar length. All right. Moving on to the third question: which of the following measures are taken for protection against corrosion? And they have given five different properties or measures, and you have to select which of the measures should be taken for protection against corrosion. The first one is corrosion resistant rebar, waterproofing, sacrificial anode, coating of rebar, addition of calcium chloride. Which of these measures would you take in order to reduce corrosion or the risk of corrosion in concrete? Yes, anyone?
Okay, I
Hi,
think it's
Tobias.
option number.
Yeah. Yes.
That is a corrosion resistant rebar and waterproofing, sacrificial anode, coating of rebar. Addition of calcium chloride. It is not coming to this case.
Okay. This
That
is
means
you need to say that.
answers 1, 2, 3, and 4. That is except 5.
So the third option is correct,
Exempted.
right?
Yeah.
Yes. Right. You're right. Thank you, Abdul. Thank you, Tobias. So yeah, the measures that you're going to take to increase the protection against corrosion are these four. Use of corrosion resistant rebars. What is corrosion resistant rebars? When you use stainless steel rebars. I mean, it's not recommended
And
because of the
this
high. Yes, go ahead.
epoxy coated steel also included in that case.
Yes,
Epoxy coated steel.
it is included because apparently they are corrosion resistant sometimes. But as I mentioned in the last class as well, these polymer coated rebars sometimes, due to their delamination, could in fact enhance the rate of corrosion. So anyway, they are marketed as corrosion resistant rebars, and but anyway, at the from the point of view of I mean, of a consultant, I would not recommend you to go ahead with these polymer coated rebars. You could go ahead with galvanized rebars or stainless steel rebars if you're able to afford that. But yeah, anyway. So yeah, corrosion resistant rebars could include stainless steel rebars or galvanized rebars and so on.
This stainless steel bar, it is very expensive, isn't it, sir?
Yeah, it is. It
For
is expensive. That is exactly
it-
why we don't use stainless steel as a
yeah,
rebar.
and
Generally, stainless steel sections are used only for, I mean, aesthetic as well as where metal is required. I mean, steel has to be used in the case of gates or grills that you might have in your structural. I mean, in your buildings. But other than that, we don't use stainless steel for the purpose of reinforcing steel. Then there is waterproofing. Why waterproofing? Can anybody answer? How could waterproofing your concrete protect us against the risk of corrosion?
waterproofing, that means just avoiding the presence of water inside the concrete. That means
Right.
there won't be any. That is the main reason. If it is waterproof, properly waterproof, that means once it is settling, I mean, it is getting dry, then try to protect the water, for to just moisturizing the concrete. It is preventing. That means if the water present is there, then only the steel oxidation, this is getting faster if it is there is moisture. If it is oxidation in the presence of water, then it will affect the starter to rusting the steel.
Right. Okay. Um, so does this mean? All right. I agree with you. Thank you. But does this mean that should we not cure our concrete? Because when we cure our concrete, we are essentially providing water into it. Now, then we are saying that we need to waterproof the concrete in order to protect the steel rebars from corrosion. So why are these contradictory statements? We want to waterproof the concrete, that I mean, sorry, we want to cure the concrete, meaning that we have, I mean, either we pond the concrete so that the whole of the concrete is fully saturated, 100% relative humidity, or and then we are saying that we need to waterproof the concrete so that the water doesn't get inside the concrete, and that will protect us against corrosion. These are two contradictory statements, right?
Normally, waterproofing is doing after getting dry the concrete. That means after finishing the curing period and all these things. Once it is
Okay.
reaching to, then only applying the waterproofing. Normally for the construction site and all these things doing like that. If it
Right.
is, water, if it is enwrapped water inside the concrete, then
Mm-hmm.
after we started the waterproofing, then it will be problem. So the enwrapped water, it will remain there in the concrete. Once
Right.
if it is waterproof, that means concrete surface, it is doing the waterproofing. That
Right.
means it will enwrap and very long time, if it is there, then it will be reverse effect for the steel. I mean,
Right.
it is started for it started to rust. Once the rust started, then
There
definitely
is
the
no
concrete
looking
started
back.
to crack.
Yeah.
Yeah,
Yeah.
because that's why normally doing the waterproofing after the this curing period and getting dry, and there is a minimum moisture inside the concrete, then only do the waterproofing. That's why some time is leaving for the waterproofing process.
Right. Right.
Normally in the site actual site conditions, it is doing like that. That is my
Right.
experience and just explaining that.
Yeah. Thank you, Abdul.
Waterproofing
You're very right.
immediately, waterproofing immediately nobody will accept. Even for the painting also, like you're doing like that. The
Yeah.
minimum moisture, there is specific moisture is there. If it is, if you do the plastering, everything done, and it is in a wet condition, nobody will prefer for the painting. Once it is exposed to all the water inside this, I mean, for the masonry or plastering, then only start the painting also.
Right.
Otherwise,
Right.
it will scale out all the paint. The
Yeah.
same
Exactly.
way, the waterproofing also doing like that. There is certain periods it is giving for the curing. Once it is finished, then only start the waterproofing.
Right.
That is a normal practice. What I understood.
Yeah, right. You're very right, Abdul. Yeah, that is exactly how you want to do it. Your apply your waterproofing compounds on the surface of your concrete after it has gained enough strength. After it has been cured for a long enough time for it to gain the strength. Then only you apply these. While applying these plasters or uh, while I mean, finishing the surface of the concrete, the final finish. Then at that time only you apply these waterproofing compounds. But anyway, why? How does um, uh, I mean waterproofing protect us against corrosion in concrete? We know that majorly corrosion occurs due to, let's say, carbonation, carbonation induced, and chloride induced. Right? For chloride ingress, there has to be sufficient moisture for the chloride ions to travel inside the concrete pores. Sufficient moisture required for chloride ions to travel inside the concrete pores. So moisture is required, water is required for chloride induced corrosion. Without the presence of moisture, if the concrete is very dry, the chloride ions will not be able to travel to the sides of the steel rebar, which is quite inside the concrete. It has to cover it has to pass through the concrete cover in order to reach those the steel rebar sites, and therefore corrosion, the rate of risk of corrosion will be reduced when there is no moisture in the concrete. Coming to carbonation induced corrosion, again, carbonation also requires moisture. Now, If the concrete is, there are two cases to it. If the concrete is fully saturated, 100% RH, then carbonation cannot occur because, and I'll come to this, why it can't occur. And if the concrete is fully dry, 0% relative humidity, then no carbonation. So when there is 100% relative humidity, we know that for carbonation, three things are essential: moisture, oxygen, carbon dioxide, right? Now, at 100% relative humidity, when the concrete is fully saturated in a fully saturated condition, the solubility of these gases, oxygen and carbon dioxide, is pretty reduced. And due to this, when the solubility of oxygen and carbon dioxide is low in water, and therefore when the concrete is fully saturated, carbon dioxide cannot get inside the concrete due to its low solubility in water, right? So no carbonation will occur. When there is 0% relative humidity, even if carbon dioxide can now get inside the concrete, but there won't be any moisture available for it to hydrolyze and form carbonic acid. So no formation of acid. Yeah. And therefore no carbonation. So carbonation induced corrosion requires a relative humidity of around 60 to 80% inside the concrete for it to affect the concrete. So both the processes that majorly govern the corrosion in concrete, that are linked to the presence of water in the concrete pores, and therefore when we apply waterproofing compounds on the surface of concrete, it will restrict the water from coming inside the concrete, and therefore it will also reduce the risk of corrosion. Now, as Abdul has rightly mentioned, these waterproofing compounds are uh, applied on the surface of the concrete after the concrete has gained sufficient strength. Um, so, after a curing period of, let's say, 14 or 28 days, and then only these waterproofing compounds are applied on the final surface after the plaster has been placed on the surface of the concrete. Then only these waterproofing compounds are applied, so that the curing is not affected. The curing of the concrete is not affected by applying these waterproofing compounds, right? Coming to sacrificial anode, what is a sacrificial anode? Can anybody say? All right. Uh, while when we make these reinforced concrete structures, we intentionally place certain metallic materials, like let's say in the case of zinc. So zinc, when we use zinc as a sacrificial anode in concrete, reinforced concrete structures, we expect the zinc to corrode, and so that the steel, the reinforcing steel, is protected. So these sacrificial anode act uh, as material to undergo galvanic cell corrosion. right? So these sacrificial anodes are intentionally placed inside the concrete so that the anode, instead of forming at the steel rebar surface, it forms at these locations, and therefore these metals get corroded. The oxide is formed, and the I mean, the use of zinc as as this galvanic for the case of galvanic cell corrosion is because the zinc oxide or the zinc corrosion product that is formed has a very less volume as compared to that of the steel corrosion product, and therefore it doesn't create any um, uh, tensile stresses within the concrete, and therefore it doesn't induce any cracking. So we use these sacrificial anodes inside the concrete so that these anodic materials get corroded while the steel reinforcement is protected. So use of sacrificial anode is also a measure against the protection of steel reinforcement against corrosion, right? And finally, the coating of rebar. Yes, sometimes these rebars are painting, galvanic coating, and so on. These rebars can be painted and coated so that they don't, the corrosion is reduced in this case. And it has to be kept in mind that while coating the rebar surface, it has to be uniform throughout the surface. If you leave certain portions and cover certain other portions, again it will result in a microcell corrosion, the corrosion within this same rebar itself, and that microcell corrosion will induce cracking in concrete. So these are the things that you have to keep in mind. So the first four statements are true, and these are the measures that you should be taken for protection against corrosion. The last one, addition of calcium chloride. Calcium chloride is added as an accelerator, so it increases the initial early strength of the concrete. So calcium chloride is used for those purposes, but it is not recommended to be used in high amounts, because then you're essentially increasing the amount of chloride concentration inside the concrete. And when the chloride concentration inside the concrete increases, that will act as the case of admixed chlorides induced corrosion. So when you are using a calcium chloride accelerated in very high amounts, that could lead to the risk of admixed chloride induced corrosion in concrete. So this is not a correct measure. So these are the four measures that you could take in order to increase the protection against corrosion, right? All right, I'll just take a break of around 10 minutes and come back. You can stay in the meeting and I'll just come back.
Okay, sir.
Hello, I'm back. All right. The fourth question in this assignment was, which of the following is correctly matched? And there are three statements given: linear polarization resistance matched with corrosion rate. Second is Nernst equation matched with potential. And the third is Volmer-Butler equation matched with net current density. You have to mention which of these have been correctly matched. This is pretty straightforward and was discussed in the lectures as well. Linear polarization resistance, what does it measure? Does it measure the corrosion rate? Nernst equation, what does it measure? Is it the potential? Volmer-Butler equation, that does it measure the net current density? And you have to mention, yeah, which of these are correctly matched. Can someone please answer this question?
It is 1, 2, and 3. All are linear polarization resistance, Nernst equations, and Volmer-Butler.
Right.
It is 1, 2, and 3. That is the answer.
Yes, that's the correct answer. All of these have been correctly matched. So these are the excerpts from the lecture slides I've taken, and The first one is a linear polarization resistance. I'm guessing that it is visible to you, or else, yes, I can. Yeah, this is the linear polarization resistance, and this is the first question of this assignment to calculate. I mean, which of these equations is given by B? So the linear polarization resistance is this, and it measures the corrosion rate. So this was related to the corrosion rate measurement. Sorry. Yeah, this is the corrosion rate measurement. So this is correctly matched. Then the second was the Nernst equation. This is the Nernst equation. And this measures the equilibrium potential. So this is also correctly matched. Nernst equation measures the potential. And finally, the Volmer-Butler equation that measures the net current density. So the Volmer-Butler equation is also correctly matched. So the answer to this correct answer to this question is 1, 2, and 3. Right? All right. The fifth question was, which of the following properties are crucial to model for cracking in concrete? And they have listed out 6 properties of concrete. The first one is elastic modulus, cover depth, tensile strength, rate of corrosion, rebar diameter, rust products density. Which of these properties are crucial to model for cracking in concrete? Can someone answer this question?
That is 1, 2, 3, 4, 5, 6. That is all are crucial. I mean,
Yes.
elastic modulus and cover depth that also affect. Tensile strength also it will affect. Rate of corrosion, rebar diameter, rust products density. In
Okay.
rust, definitely the volume it is increasing. If it is there is rust in the steel, then definitely the volume will increase. Then it will damage. That
Right.
means crack will fall.
Right.
Rebar diameter also is changing due to the rust. Rate
Right.
of corrosion that also will affect. Tensile strength, that means the volume it is increasing. That means the surrounding area it is tensile force is acting on the concrete. Then
Right.
crack will develop. Cover depth also. Cover, if it is insufficient cover, then definitely it is easy to get a corrosion. Then again the same effect will happen. Elastic modulus also.
Right.
All are correct. That means 6 statements.
All of these are correct.
Uh, yeah. Yes.
Yeah. Thank you, Abdul. Yeah, that's the correct answer. So let's go over these properties one by one. First is the elastic modulus. Just give me a moment. Just give me a moment. Yeah, the elastic modulus.
Elastic modulus of elasticity in the concrete.
Yeah, modulus of elasticity in concrete. So that is that will govern the cracking in concrete. How? Because elastic modulus will also govern the fracture strength, right? That means the stress at which the concrete will undergo a fracture or rupture. And that is important because when there are tensile forces getting developed inside the concrete due to the deposit of corrosion products over the rebars, there is a volumetric expansion, and this volumetric expansion induces a tensile stress inside the concrete. Now, due to this tensile stress, the concrete will start cracking, but that will again depend on the elastic modulus of concrete. At what level of stress will the concrete show signs of cracking? So elastic modulus is an important property to model the cracking in concrete. Then there is cover depth. Cover depth is required due to the fact that the higher the cover depth, the rate of corrosion and the age at which the propagation, I mean the initiation phase and the propagation phase of corrosion will take place, that will be governed by the cover depth. Because higher the cover depth, lower is the risk of corrosion, lower is the uh, um, uh, risk of ingress of ions from outside the concrete. So that will protect the concrete. Higher cover depth will protect the rebars against corrosion, and therefore cover depth has a role to play while predicting the cracking in concrete. So that is one factor. As we discussed, again, tensile strength of the material will also govern it, because essentially there are tensile forces or tensile stresses getting developed inside the concrete due to a volumetric expansion caused by corrosion, and therefore tensile strength of the concrete will also be a major factor for modeling the cracking in concrete. And finally, the rate of corrosion. Higher is the rate of corrosion, higher is the rate of deposit of these, higher is the rate of formation of these corrosion products which have a high volume, and therefore there will be a larger stress produced within the concrete within a short span of time, and that will be a factor in modeling the cracking of concrete. So rate of corrosion, higher the rate of corrosion, higher is the uh, rate of deposit of these rust products, and therefore higher is the risk of cracking. Rebar diameter again, because ultimately it is the corrosion, the cracking coming from corrosion could be due to two ways. One could be due to the volumetric expansion caused by the deposit of this corrosion products, as we discussed, and the other could be due to severe loss of the rebar cross section, that leading to a structural failure. So one the cracking in sorry, corrosion induced cracking due to corrosion could be due to two reasons. One is due to volumetric expansion, and therefore not eligible at all. Volumetric expansion, and the other reason could be, and this is a material failure. It's a material failure, and the other one could be severe loss of cross section rebar cross section. When there is a severe loss of the rebar cross section, initially the rebar that has a um, that has a diameter of d, let's say. Now due to corrosion, the rebar has an effective diameter of, let's say, d, where d is less than d, small d. So now, initially the structure was designed with a strength carrying capacity for this diameter of the rebar. But now, since the diameter of the rebar is reduced due to corrosion, the load carrying capacity of the rebar will also be reduced, and therefore this could lead to a structural failure, and that will end up in cracking the concrete. So rebar diameter has also a role to play, and in fact a major role to play in the case of cracking of concrete. And you can see this slides that I have taken from the lectures, and here the D is the rebar diameter, right? So whenever you're modeling a corrosion propagation period, be it the propagation period or be it the cracking period, which follows the propagation period, the rebar diameter has a role to play. And finally, rust products density. Yes, again, the denser the rust products are, there will be a lower volume expansion, and therefore the risk of cracking could be lower. But when the rust products are lower in density, have a low density, then they'll occupy a larger volume. And when they occupy a larger volume, they'll induce a larger amount of stress. So the density of the rust products and the amount of rust products that are being formed at a given region inside the concrete, that will also govern the cracking in concrete. So all these properties are important in order to model the cracking in concrete, right? Moving on to the sixth question, what is the minimum cement content and cover depth recommended for the extreme exposure conditions in the Indian standards? You have to say the minimum cement content for exposure conditions being extreme and the minimum cover depth recommended in the Indian standards. Yes, can someone answer this question?
As per Indian standard 456 2000, that is, it is mentioned is 360 kilogram cement content and 75 mm
75
uh,
mm cover depth.
covered up. That is as per IS
Right.
456 it is mentioned.
Yes. Thank you, Abdul. You're right. This is as per the Indian standards IS 456 2000. The table 5 in this Indian standard states the different minimum cement content, the maximum water to cement ratio, and the minimum grade of concrete allowed for different exposure conditions of the site and for normal weight aggregates, not for lightweight aggregates. This is for normal weight aggregates and of 20 nominal maximum size. So they have also provided you with different correction factors when you the nominal size of aggregates is varied from this value. That comes in the next table, I guess, table 6 in the Indian standards. But anyway, that is not relevant to us. What is relevant is when the exposure conditions are extreme, for reinforced concrete structures, the minimum cement content is 360 kgs per meter cube. And that is from a durability perspective. Because when the cement content is low, the strength will be low and there will be a higher amount of higher porosity in the concrete. When there is a higher porosity in the concrete, it will and the pores will also be coarser in nature and that will reduce the durability of the concrete structure. So from durability point of view, the code has prescribed a minimum cement content and that is 360 kgs per meter cube of concrete for extreme exposure conditions. And then there is a nominal cover to meet the durability requirements given in table 16 of the Indian standards IS 456. And then again for extreme exposure conditions, the nominal concrete cover is should not be less than 75 mm. So the minimum concrete cover is recommended as 75 mm for extreme exposure conditions, right? Moving on to the seventh question, which of the following is characteristic to the high performance concrete? So now we have moved from the durability aspects of concrete to a different kind of concrete in itself. It is a high performance concrete. And this was towards the last two lectures of this week. So which of the following is a characteristic to the high performance concrete? Continuous grading of aggregate, use of coarse pozzolanic materials, high water reducing admixtures, high porosity. Which of these are recommended or characteristic to high performance concrete? These kind of properties are generally seen in the case of high performance concrete. Can you answer this question?
That is continuous grading of aggregate, use of coarse pozzolanic materials, high water reducing admixture. High porosity is not considered. That is 1, 2, and 3 characteristic to the high performance concrete. These
Use of
three
coarse
first
pozzolanic materials, you say?
continuous grading of aggregate. That is
Yeah,
first
that is
one.
the
The
first one.
first one. Use of coarse pozzolanic materials. That is second. And third, high water reducing admixture. High porosity is not considered for this one.
Okay, this is wrong, of course, because high porosity is not recommended. But why would you say how does using coarse pozzolanic
This,
materials?
that is use of coarse pozzolanic material.
Yeah, coarse
That means
pozzolanic
I think
materials means higher size of materials or larger size, right?
then I think this use of coarse pozzolanic material, this workability will be more, isn't it?
Okay.
consistency will be more than that's why it's a very dense concrete to produce.
So
And one more thing, sir. This answer in I applied this one. I mean, answered this one. This first, second, and third. This was the accepted answer. I got the answer.
okay, they have given the 1, 2, and 3 as the correct answer.
Yeah, yeah. High
No,
porosity, of course. High porosity means
of course, high
definitely it won't be.
porosity is not, yeah, not a
It is
characteristic
not
property.
a dense material. That means density will be less, and the then porosity. That means strength will be less, definitely,
No, I think
because it is
only
porous.
1 and 3 are the correct answer to this question. And I'll tell you why. Because if
Yeah,
you have also looked at the lecture slides, it was
yeah.
discussed with you that
Mm.
fine pozzolanic materials, they cause a pore structure refinement.
Yeah, coarse
They have a,
crystalline material.
yeah, they have
Mm.
a bifold enhancement in the properties of concrete. One is the pozzolanic reaction, of course. So the pozzolanic reaction, and therefore extra additional CSH, increase in strength, right? And then when the second is a fine, using the fine materials, it results in a pore structure refinement, meaning that they make the pores fine in nature, finer pores and reduced pore connectivity, and therefore enhanced durability. So it is always recommended to use fine pozzolanic materials in your concretes, because anyway, yeah, as you mentioned, it could, a coarser pozzolanic material will end up giving you a better flowability as compared to that of finer pozzolanic materials, because as the material becomes finer, it will have a larger surface area and therefore a larger water demand. So the flowability of the concrete will essentially get reduced. But the flowability or the rheology of concrete is not just governed by the size itself, it is governed, in fact, by the size fraction and the grading of the total, or all the solids in the mixture. So, therefore, instead of just mentioning that a coarse material need to be used in order to ensure a better flowability, you could mention it that a well-graded material or a continuous grading of the aggregates has to be ensured in order to achieve a better packing, because a continuous grading of the aggregates will induce a better packing. So therefore, you'll have a good strength to workability ratio. So for the same workability, you'll achieve a greater strength due to the better packing, right? So a continuous grading or a well-graded solid system has to be used in order to achieve a better rheology without compromising on the strength. When you use these coarse pozzolanic materials, first, using a coarse pozzolanic material will reduce the reactivity of the pozzolanic materials, because coarser the material, lower will be its dissolution rate inside the concrete. And since these pozzolanic materials, let's say in the case of fly ash, these are already very slow reacting materials. When you make them even coarser, the reactivity will, the rate of reaction will become even slower. So the reactivity will be reduced. And again, when these materials are coarser, they won't be able to provide you with the kind of post structure refinement that a finer material will give you. So use of coarse pozzolanic materials is not recommended. And then high range water reducing admixtures are used in the case of high strength concretes, so that you can reduce the amount of water. For the same flowability. For the same kind of slump or flowability, the water requirement will be reduced by the use of high range water reducing admixtures. So this is again recommended. Again, high porosity is not a characteristic property of any kind of good concrete, in fact, because higher the porosity, lower will be the durability, lower will be the strength as well. And the two main characteristics of high performance concrete is its greater durability and greater strength. So I think 1 and 3 are the correct answer. If they have given 1, 2, and 3, then I'll get in touch with them and they may, I mean, the team will correct it. The 1 and 3 are the correct answers in this question, right?
Sir, normally for this high strength, high performance concrete, that compressive strength is coming ranging 60 Newton to 80 Newton, isn't it?
Beyond
Yeah, yeah, 60.
60 megapascals,
Beyond 60, it is considered for the high performance concrete,
high
isn't it?
strength concrete.
Sometimes
Yes.
for this high performance concrete for workability, air entrapping agent also optional, isn't it?
So I'll tell
Air,
you the first difference between a high performance concrete and a high strength concrete. The strength criteria that
uh,
you are mentioning on the basis of greater than 60 megapascals,
yeah.
whenever a concrete has a strength higher than 60 megapascals, that is called a high strength concrete. A concrete becomes only a high performance concrete when it has a higher strength and a greater durability as well. So it has to pass the durability aspects as well, like a reduced rate of corrosion, an increased resistance to chloride penetration, an increased resistance to carbonation. So then only a concrete be called will be called as a high performance concrete because it has a higher strength as well as a higher durability. When it is only given in terms of megapascals, I mean a strength terms, that is only called a high strength concrete, greater than 60 megapascals. When it is beyond around 120 megapascals or so, I mean it varies from region to region, but it goes from when it goes from 100 to 120 megapascals or so, it is called a ultra high strength concrete. And generally,
These type of these
these
type of
two,
concretes are developed recently, I think, isn't it? Not like
yes,
traditionally. Yeah, these recent developments are not this thing. Maybe
yeah, I mean,
10 years, something
yeah,
like
within
that.
a decade or so, yes. Because so I'll tell you why these two terms are used synonymously, because when you increase the strength, the increases in strength comes from the pore structure refinement when the porosity is reduced and the pore sizes are also reduced. And when the pores porosity and the pore sizes are reduced, then the durability is also enhanced. So ultimately, a high strength concrete also ends up being a high performance concrete due to its enhanced durability as well. So that is exactly why these terms are used synonymously, but there is a difference. I wanted to mention that. And yeah, as you mentioned, these type of high strength and high performance and ultra high performance concretes have been developed very recently. In these cases, in the case of ultra high performance concretes, in fact, you will have to add some additional additives like let's say fibers, steel metal fibers or polymer fibers, in order to increase the strength even more. So yeah, these kinds of different types of concretes have been developed very recently, and the purpose of using these kind of concretes is to reduce the, the size of the member requirement. So the structural
Yeah,
members
the structural structural constraint. I mean, for certain area for architectural view and all these
right,
things, some
exactly.
reducing the sizes and all these things. That case, it is using this
Yeah, not just
high
from
strength concrete.
architectural point of view, but also when you reduce the size of the member, effectively you're also reducing the self weight of the
Yeah,
structure. So you're making your
that
structures lightweight in nature. So that
No,
will
that means it is slightly different than the balanced section of the concrete. If it is a balanced section, concrete and the steel, it is just like a balanced section. In case some constraint conditions, then it won't be balanced. But sometimes the steel also taken some compressive strength. In that case, it is using, isn't it? That
no,
means
it will again be
mainly.
the concrete structural design will be the same. It will be a balanced section or a under reinforced section majorly. We always want the steel to govern, right? So the structural design will be the same. Only when you are increasing the characteristic compressive strength of the concrete, what you are doing is essentially reducing the size of the members, right? The amount of thickness of depth for a given structural member that you are required to provide with a certain kind of concrete of a low strength, let's say 30 megapascals. Now the with the use of a high strength concrete 60 megapascals, the size of the members, the width and the depth of the members will be reduced. Requirement will be reduced because we'll be able to achieve the same moment of resistance with a reduced size of the member, right? But the structural design doesn't change as long as you're using the steel reinforcements inside the concrete. The structural design doesn't change. When you're talking about ultra high performance concretes and the newer engineered cementitious composites, the engineered cementitious composites have a very high flexural and tensile strength in them. They do not require a steel reinforcement as such. So at that time the story is very different. But when you're using your steel reinforcements in the concrete, it always has to be an under reinforced section or a balanced section kind of a design. Never an over reinforced design, right? The structural design remains the same. Only you're increasing the strength of the concrete, and therefore you're allowed to reduce the size of the members. I hope that was
Yeah,
clear.
I got.
Yeah.
Yeah, yeah,
Okay.
yeah. It is clear.
Okay. Thank you. Moving on to the eighth question. It is an assertion and reason kind of a question. So the assertion is that five properties of the high strength concrete are poor than normal concrete. And the reason they have given is at high temperature, water vapor will try to escape the cement matrix. Since in high strength concrete, pores are coarser, it will lead to more cracking. You have to mention if the assertion is true and the reason is true, and if the reason is the correct explanation of the assertion or not. Can someone please answer this question? Are the five properties of high strength concrete poor or good than normal concrete, and why?
This assertion is true, but reason is false.
Okay. Why is the reason false? Can you also explain?
Reason high temperature water vapor will try to escape the cement matrix. Since in high strength concrete, pores are coarser. But high strength concrete pores are less. So
Yes.
that means water entrapping will be less in that case because it is high strength concrete. It is very very dense concrete. That means the strength of concrete pores are uh, coarser. It is not coarser, maybe
It is
finer.
finer. Yes. Right.
Yeah,
Yeah,
that
correct.
is the reason. That's why it is false.
Yeah. Thank you, Abdul. So the answer to this question is assertion is true, but the reason false. Reason is false. And why so? It has been seen that when you use high strength concrete in your structures, the fire properties are reduced. I mean, the fire performance is reduced. Why does it happen so? Because in the case of high strength concrete, as Abdul has already mentioned, the pores are finer. When the pores are finer, and there is still some pore water present in the concrete matrix itself. When the concrete structure is exposed to high temperatures, this pore water that is present in the smaller pores will vaporize, will turn into steam. Now, when the vapor pressure inside those concrete pores increases, that will induce a stress. But again, in the case of high strength concrete, since the pore connectivity is also less, therefore the vapors, the water vapors inside will get trapped inside the pores and will not find a way to escape out of the structure. When this vapor pressure is increased to a very high level and the vapor is not being allowed to escape from the structure, that will cause a explosive spalling in the structure. So that is exactly why we have seen that high strength concrete have a poor performance to fire properties. So in normal words, I'll just draw something to explain you. Let us say this is a normal concrete member and these are some concrete pores, right? So these are some concrete pores and this is normal concrete. So you see that the pore sizes are also coarse and the pores are also connected. When there is water inside these pores and it vaporizes when the temperature is increased, this vapor can now has a path to escape from the concrete and therefore the vapors can escape from the structure of the concrete, right? So when the vapors get released from inside the pores of the concrete, that will reduce the stress concentration. Compared to that, in the case of a high strength concrete, the pores are now much finer and also the pore connectivity is also reduced. And therefore, whatever vapor is being formed, that will get trapped within the concrete itself and will not find a way to escape from the concrete. And due to this entrapping of the vapors, once the temperature increases to a very high level and therefore the vapor pressure also increases to a very high level, that will cause a explosive cracking of the concrete and the release of the vapors. So this is known as explosive spalling in the case of fire exposure, right? So yes, the assertion is true. Fire properties of high strength concrete are poorer than that of normal strength concrete, as the vapor pressure in the case of normal concrete is allowed to release, whereas in the case of high strength concrete, the vapors are trapped inside the concrete small concrete pores, and therefore that causes some explosive spalling in the concrete. And the reason is false because the concrete pores in the case of high strength concrete are finer in nature, and due to this finer pores only, it is not able to escape, and due to the reduced pore connectivity as well, it is not able to escape, and that is causing the spalling in concrete. All right, so the answer to this question is the third option. Moving on to the ninth question, marsh cone can be used for determining the plasticizer compatibility but not the mini slump cone. Is it a true or a false statement? It's a very straightforward question. Marsh cone can be used for determining the plasticizer compatibility but not the mini slump cone. Is it a true or a false statement? Yes, can someone answer, please?
It is false.
Okay, and why so? Can you please explain? All right. Yes, you're true. You're right, Abdul. It is a false statement. So both marsh cone and mini slump cone tests are used for testing the plasticizer compatibility with cement. Marsh cone is essentially is a conical flask with a small orifice at the bottom, and then a cement paste with superplasticizer in it is poured into this conical flask to a certain level, and then this orifice is released. So the cement paste will flow down, and it is collected in a container, and the time taken for 1 liter of the cement paste to flow out is noted, and that will be the flow time of the cement paste. So essentially, uh, if you plot the admixture dosage versus the flow time, you'll see that at lower admixture dosage, the flow time will be high, but with increase in the admixture dosage, the flow time gets reduced until a certain point beyond which the flow time doesn't reduce much, and that is known as the saturation dosage, right? Similarly, in the case of a mini slump cone, it is essentially a box with a conical, I mean truncated conical shape inside it, right? So this is a hole, and this is a truncated conical shape inside it, and you pour cement paste with super plasticizer into it, and then you lift the cone, and on non-absorbing surface, the the spread of the cement is measured, and this spread diameter is plotted against the admixture dosage. Now, if I just draw another axis over here, mentioning the spread dosage, this is a continuous line, and this is a dotted line. So at lower admixture dosage, the spread will also be, sorry, the slump spread will also be low, and at higher dosage, it will increase and finally assume a constant value. So until a point, which is also again called as the saturation dosage. So based on this, you'll be able to decide at the compatibility of the plasticizer with that of the cement of a given type of cement. How do you decide that? When the saturation dosage coming from the flow time and the saturation dosage coming from the spread are more or less similar, meaning that the flow time is an indicator of the viscosity of the cement paste, right? And the spread is an indicator of the yield stress in the cement paste. So when the saturation dosage from both the tests are similar, it means that the viscosity and the yield stress both are modified in a similar way. When the saturation dosage are coming from both the tests are very different, then it means that the plasticizer is only able to control one of these properties. Either it is reducing the viscosity significantly, or it is reducing the yield stress significantly, but not both of them at the same time. Again, these tests are also used to decide the sensitivity of the superplasticizer. How do you decide the sensitivity of the superplasticizer? At a very small increment increment in admixture dosage, how does the flow time and spread values vary? So if the variation is too significant, then the plasticizer is too sensitive to a change, and therefore you'll not have a great control over the plasticizer and for the given type of cement. So when you don't have a great control over the plasticizer, then it might cause the problems of instability in the cement or concrete, meaning that it will cause problems of bleeding or segregation in the cement or concrete. So you need to also have a good sen- for the plasticizer to have a good compatibility with a given type of cement. You need to also have a good control over the plasticizer dosage. So a sensitivity aspect will give you that idea of how good how good a control you have over the plasticizer dosage. So this is how you determine the plasticizer compatibility with a given kind of cement using the marsh cone flow test and the mini slump cone test, right? So the correct answer is false. Both of these tests are used in combination with one another in order to assess the plasticizer compatibility, right? Moving on to the final question of this assignment, it is again an assertion or reasoning kind of question. In self-compacting concrete, volume of coarse aggregate is reduced. And the reason is, as for the flow, we need high mortar and paste content in SCC so that the coarse aggregate just stay embedded in them and flow along. You have to say if the assertion is true, is the reason true, and is the reason the correct explanation of the assertion or not. Can you answer this question? Yes? Anyone? In self-compacting concrete, volume of coarse aggregate is reduced. Yes, Abdul. Go ahead.
Assertion and reasons are true, and reason is correct explanation of assertion.
Right.
That is
Yes.
A.
Okay. Yeah. Thank you, Abdul. Yes, you're right. In the case of self-compacting concrete, the volume of coarse aggregates is reduced, and that is compensated by increasing the volume of sand and increasing the uh, paste content in the mix. Because in the case of self-compacting concretes, we design the mixture, concrete mixture, based on the powder content. And the powder content comes from the cement. If you look at this, look at the mixed design Indian standard IS 10262 2019, you'll find this. The powder content is the cement plus the proportion of sand passing the 75 micron sieve, right? So when uh, you want to achieve a certain degree of spread, let's say uh, anything beyond any concrete having a spread more than 500 mm, given that the concrete is non-segregating and non-bleeding, then it is called a self-compacting concrete. Now, if you want to achieve, I mean, this is not the only sole parameter in order to characterize a self-compacting concrete. It has to have a passing ability through the reinforcement. So you have to do a L box test, you have to do a slump flow test, you have to do a V funnel test, and then only the T500 times the V funnel flow time and the L box test results will also give you the based on these results only you'll be able to decide what kind of a self-compacting concrete is it, right? So there are also different categories of self-compacting concrete, and if you want to achieve a greater slump flow in your self-compacting concrete, then you need to increase the powder content in the mix. And the powder content will come from the cement and the sand. So when you're increasing the cement and the sand content in the mix, essentially you're reducing the volume of the coarse aggregates. So the assertion in the case in this question is true. In the case of self-compacting concrete, volume of coarse aggregate is reduced. Yes, and as for flow, we need high mortar and paste content in the SCC. Yes, in order to achieve a higher flow, because the reacting part in concrete is the cement paste, and the powder coming from the sand will enhance the matrix yield strength and viscous drag in the concrete mix, and therefore it will be able to drag the concrete aggregates or the coarse aggregates to a greater diameter. So you'll be able to achieve a larger flow in the case of higher powder content in the SCC. So it is the high mortar and the paste content in the SCC that ensures a greater flow in the SCC, and the concrete aggregates are only just embedded and remain as a suspension in the SCC. They do. I want to again emphasize on the fact that for a concrete to be called an SCC, it doesn't just have to achieve a certain amount of flow, but it has to stay stable. It has to have a high resistance against bleeding and segregation. So for that to happen, the coarse aggregates have to remain in suspension, just embedded in the matrix of cement paste and the mortar. So the assertion is true, the reason is true, and the reason is also the correct explanation of the assertion. Right? So that ends the
Uh,
yes, yes, Abdul.
in this case, maximum size of the aggregate. What is the maximum size of aggregate using for this SCC? I
Okay.
mean, it is nominal size. The maximum it is within less than 20 mm, isn't it,
Major,
sir?
yeah, mostly
Because
less than
yeah,
20 mm. I mean, even with
because
20 mm aggregates also, we face a lot of problems. You have to increase the powder content to so high levels in order to have that, yield stress and yield stress in your paste, so as to hold the coarse aggregates in suspension. So 20 mm aggregates also cause a lot of problems, but we can still achieve
uh,
SCC mixes with 20 mm aggregates. But it is
uh,
always
uh,
recommended that the nominal maximum size of aggregates should be less than 20 mm. It should be around 12.5 mm or 10 mm aggregates max.
if it is well graded 20 mm, then it is okay, isn't it? Well graded means less than
Yeah,
20
you're
mm.
talking about the all in aggregate
Yeah,
grading.
yeah,
Yes.
well graded,
Yes, all
well
that is
graded.
what I'm talking about. Well graded as in all in aggregate grading should be, and the nominal maximum size should be 20 mm. So it should have a good amount of good proportion of aggregates ranging from 10 mm till 20 mm, ranging from in fact 4.75 mm till 20 mm. Right?
And this concrete absolutely not using vibrator, isn't it?
No, there is
Vibrate.
no need for
Uh,
external vibration or external compactive effect.
yeah. Then
That is exactly why
if
it is
we
called self-compacting.
yeah, if we use vibrator, then segregation will be more in that case, isn't it?
Yeah, it could result in segregation.
Yeah, that means it is disturbing the concrete
Yes.
for
Yeah,
matrix.
yeah.
Yeah.
So there are
And
also
for
different
this
type of
one,
different grades of self-compacting concrete. One is a normal self-compacting concrete, and there is a self-leveling self-compacting concrete. So when you
yeah,
pour
yeah,
it
yeah.
into the formwork, it should level itself on its own. I mean, you did not provide any troweling action to level the surface of the concrete. So that is called a self-leveling concrete as well.
Yeah, that is the water cement ratio will be high in that case, isn't it?
No, it is. I mean, with the correct use of different types of powders and finer materials, like different pozzolanic materials, you'll be easy. It'll be easily able to, uh, you'll be easily able to produce self-compacting concretes at lower water to cement ratios as well. Like I personally, I have uh, designed SCC mixes at zero point 0.3 water to cement ratio as well.
Point three, that is very less only. Point
Yeah,
three.
you can still go lower, but again,
Yeah.
near the powder content will be high, the paste content will be high, so the cement requirement will also go high. Admixture requirement will also go high because you're increasing the powder content in the mix. So the essentially the cost of the concrete will increase. But yeah, you'll be able to produce SCCs at lower water to cement ratio. And in fact, I have seen that at lower water to cement ratios, the SCC mixes are more robust. Robust meaning the problems of segregation and bleeding is reduced at lower water to cement ratios because you're increasing the powder content so much that the risk of segregation and bleeding is reduced. When the water to cement ratio is high, that creates a problem to produce a self-compacting concrete mix because then you'll have to trade off between the amount of admixture you want to mix so as to achieve a certain degree of spread flow and to reduce the segregation, because if you increase the admixture content to achieve a higher spread, then it might lead to a higher segregation as well. So you'll have to find a perfect balance between these two properties, the segregation and the spread that you want in your concrete. So this problem occurs at high water to cement ratios because already the the paste viscosity and the yield stress is so low because of the higher water content. But at lower water to cement ratios, already the water content is so low, whenever you're just keeping on adding admixture, it only disperses the cement even further. It disperses the powder even further, and therefore you're able to achieve a greater flow without any risks of segregation or bleeding. Right? Perfect.
Yes, sir.
Yeah. So that ends the this assignment question. If you have any questions, then we have 10 minutes, around 10 minutes left. The session will go until 8 p.m. We can discuss your doubts if you have any of them. Otherwise, you're free to leave and we can close the session for today. We'll have a last extra session on 18th from 6 to 7 a.m. It'll be posted in the portal, I guess, and you'll be sent a mail. Yes, does anyone have any questions?
This self-compacting concrete mainly where they are using mainly. Is it using for the framed structure and all this thing? I think it is not using.
Generally, it is used in areas where the reinforcement congestion is very high, like in the case of a raft foundation, or in the case of a slab design, where the reinforcement congestion is too high. There you cannot provide an external vibration because you'll not be able to penetrate even if with a needle vibrator kind of a thing, you'll not be able to penetrate it to those areas, and you'll not be able to provide a good compaction in the concrete. And in those cases, this kind of SCC mixes come in handy because the concrete is very flowable and it is self-compacting, so you did not provide an extra compactive effort. You just have to pour it from one end, and it will move on its own through the uh, reinforcing bars, and it will cover the whole formwork area. Right?
Okay.
Yes. But in the case of self-compacting mixes, one of the major problems is could be, I mean, not is, it could be a low early strength because when the powder content is so high, you're using a high amount of admixture or superplasticizer, and that retards the cement reaction. So the early strength is sometimes reduced, but then you can also come up with different kinds of accelerators, or you can use this kind of mixes where you don't need to remove the formwork within a short span of construction.
If it is using self-compacting concrete for the slabs and all these things,
Yes.
then there is a tendency for surface crack and all these things. Is it
Uh,
chance for get
yes.
surface crack?
Yes, you're right, because the cement content is high, and therefore it could result in a higher amount of shrinkage, and a higher amount of shrinkage could lead to high risk of cracking. So yeah, it could happen. So generally, before applying these kind of concrete mixes in the field, it is recommended that you get it tested in a certified laboratory first for these properties, cracking or shrinkage and all these properties, so that you won't face it in the real structure. Yeah. But sometimes what they do is, instead of using all the powder material as cement itself, they replace some of the cement is with pozzolanic materials or fillers like limestone powder or quartz powder or fly ash or slag powder. And these reduce the risk of shrinkage cracks, because essentially the cement content is also reduced due to the inclusion of these kind of materials. So that reduces the shrinkage cracking, risks of shrinkage cracking.
That means the Pozzolana cement is
Better.
favorable, isn't it?
Yes,
Yeah.
yes.
But the only thing is the initial setting time will be more
Initial
for the
setting time,
Pozzolana cement.
initial setting time, and the initial strength will also be a little lower.
Yeah, that's right.
Yes. We could use it
Okay.
with the with an accelerator in order to modify the setting time and the early strength as well.
That means additional admixture.
Yeah, additional
Normally
admixture
for the
for so
normally for this admixtures is not recommending for the structural design. No, this is not recommending, only in avoidable cases only suggesting for the admixtures. Normally, structural engineers not recommending for the admixtures.
I
Some
mean,
cases, if it
yes,
is
it used to be the case. It used to be the case 10, 15 years back that since the understanding of the chemistry of admixture and the reaction of how the cementitious reactions undergo under the action of these admixtures was not developed to these levels. Therefore, previously the engineers and the consultants didn't recommend the use of admixtures until and unless required very much on the site. But nowadays, it has been seen and it has been proven through scientific research that use of superplasticizers or chemical admixtures can, in fact, enhance the strength and durability in your concrete somewhat. So, the right amount of admixture is important rather than using not using the admixture. If you use the right amount of admixture and the right kind of admixture, then you'll be able to achieve a greater performance of your concrete as compared to a concrete which does not have any chemical admixture in it. But yeah, you're right. It
that
used to be
means,
the case 10, 15 years back. Nobody was, I mean, there was a high reluctance on using chemical admixtures in concrete structures. I hope that answers. Mm, yes.
okay, sir. Thank you very much. Any next 18th, there is one more session is there in 7
Right.
to 8, isn't it?
Yeah. 6 to
Okay.
7.
Then
I guess 6 to 7. It'll be
six.
posted on the link
Oh,
on the portal anyway.
oh, oh, 6 to 7. Okay.
Yes.
Okay. Thank you very much for your class, and it is very, very nice, and really appreciating.
Thank you.
Anyhow, Okay, we will see one more session in 6 to 8. Right now, I am just leaving.
Yeah,
Thank you very
thank you,
much,
Abdul.
and
Have a good day.
good night.
Good night. Bye bye.
Okay, okay, thank you, sir.
All right, we are closing the session for today. We'll meet again on, for the last session on 18th.